Okay, any questions about what we've been talking about since yesterday? All clear, great. All right, so yesterday we okay, yesterday we talked about random number generation, which is a whole topic in itself. The important takeaway for that is just that we can assume that we have we can have the raw materials for creating the random variables that we want. In other words, the random number term applies to independent, identically distributed, uniform 0-1 random variables. That's it. And that's the raw materials from which we're going to create other distributions. And that's what random variate generation is about. So today, I'm going to introduce the really kind of the workhorse way to do that. It's called the inverse transform method. And it involves, well, just kind of reviewing a little bit of some probability. You've all had that at one point or other. And so, so this, at least some of this should be reviewed. So, okay, so we can assume we're given this sequence of IID uniform 0 random variates. So, and well, nobody has asked about this, but been using the term random variate as opposed to random variable. The reason for that is that when it is pseudo-random as generated by the computer, it's not truly a random variable. So we call them random variates to indicate that we're aware of the fact that they aren't truly random. So a random variate is kind of like a random variable, only not literally. And I didn't make that up. So if you have complaints, sort of take it to whoever. I'm not sure who did that, so I'm not sure who you can complain to. But anyway, so all right, so that's what we have, and we want to provide a sequence, another sequence of random variates having a given, and I'm going to say CDF, and now when I say CDF, does that ring a bell? Do y'all know what that is? Cumulative distribution function. Not to be confused with two other functions, the probability density function or the probability mass function. So are those, you're all familiar with those terms. Okay, so now the thing to understand about these functions, such as the reason focusing on a CDF, or there are actually two. That is the function that we're going to be using to create the transform for our random variables. So that's what it is. But there's kind of a second reason, and that is that every random variable, now we're kind of in the random variable range, but every random variable has a CDF. Every random variable has a cumulative distribution function. Why? Because it's defined, the definition of the cumulative distribution function is defined that the probability that that random variable is less than or equal to some function. So, and because every random variable, for every random variable, you can compute this quantity. I mean, that's sort of the definition of the random variable. So this always exists, regardless of what kind of random variable you have. However, if you think of the probability density function, which is actually kind of a little redundant, some people call it just a density function, but probability density function, PDF, Not every random variable has one. For example, only continuous random variables have a PDF, a probability density function. On the other hand, discrete random variables have what's called a probability mass function. And not every random variable has that. And for example, no continuous distribution has a probability mass function because there's no probability mass anywhere. And you probably will recall from probability that if you have a continuous random variable, let's say we have like our good old friend, the normal, and pick a value. What's the probability that a normal random variable is exactly equal to this value? 0. In fact, for every continuous random variable, the probability that it's exactly equal to any particular value is 0. That's part of what actually defines a continuous random variable. On the other hand, if you have a discrete random variable, it will take on sort of finitely many values, and it will have like a mass function that you can sometimes graph looking like this. And so for that, what's the probability? If this is X here, there is a positive probability that this random variable is exactly equal to this X. So if I have like a Poisson random variable, there's a certain probability that it's exactly equal to 0 or exactly equal to 1, etc. So now you may be under the impression, therefore, that every random variable has either a probability density function or a probability mass function. And you would be wrong, because there are these ones that don't have either one. Specifically, they're actually mixed distributions that are partly discrete and partly continuous, and they have there are actually applications in nature for something like that. I don't know if you can think of one, or did they talk about that in your probability class for some reason? No. Supposing my random variable is the amount of rainfall that falls on Watkins Hall in every 24-hour period on any given day. That's, now first, is that going to be a random, or is that going to be a constant? Probably going to be random, because now on the days that it rains, would you characterize the days that the amount of rainfall in the days that it rained as a discrete or a continuous thing? It makes more sense to be continuous. Why? Because if I can measure exactly how much, it's going to be pretty much any value. On the other hand, on days like today, what would be the observation? 0. In other words, that random variable has a probability that its value is 0. And on times when it isn't 0, it's, there's no, for the non-zero ones, it's kind of continuous, but for the 0 ones, so that is neither a discrete nor a continuous random variable. I mean, it's kind of a mixture. And there are random variables like that. So not every random variable has a probability mass function or a probability density function. And if you hang out amongst the sort of weird mathematical types, as I once did when I was in grad school, there are even weirder ones. There are ones that are just totally strange, that you don't want to know about because it's the stuff of nightmares. So anyway, but regardless of any of that, every random variable has a CDF. For that random variable I described, we could define a CDF for that. A cumulative distribution. Why? Because you can always define this function as a function of x, little x. Now, one thing that sometimes students coming out of the probability courses tend to be a little confused about this. Some of it is due to the notation, and for the notation, you have to kind of pick your poison. So here, notice that I've kind of put x, the big X, as a subscript, partly because in probability, usually we're only dealing with one random variable at a time. But here we're going to be dealing with more than one. In fact, right away we have more than one. We have these uniform ones, and then we have this other one. So the other thing to understand is that, okay, so while capital X is a random variable, this is just a formal argument of a function. I mean, it's like the argument in a method, in Java or Python. It's just a label for how you define what this is. And the other thing is that there is nothing random about this function. This is a deterministic function. What's random is the random variable. So if we perform an experiment and draw from that random variable, however we do it, whether we do it physically, whether we do it on the computer in our simulation, the value that we get is going to be, well, random. We can't we can't say which one it's going to be beforehand. All we can say is the probabilities, or we can describe the probabilities. It will either be of certain values if it's discrete. So if we roll a fair die, we can say I don't know what the roll is going to be, but I know that each side has a probability of 1 in 6. So if I roll it many times, then I'll roughly get the same amount on each of those. Okay, but there's nothing random about this function. It's a deterministic function. It simply describes these probabilities. Okay. Now, I'm not going to torture you with the things that the probability course did with the balls and urns and stuff like that, but because having already gone through that, then you have all that under control. Okay, so why do that? Because what we're heading up to is this inverse transform method, and we're going to work with the CDF. So if I say I want to generate exponential random variables, for example, then I need to, with this method, I need to start with what is the CDF of the exponential distribution, or more generally, what is the CDF, the cumulative distribution function for the random variable that I want to generate from. Okay, so that's what we're going to work with. And as I said, this is just a normal function. There's nothing random about this. In many cases, we can actually write this down. And for the cases where we can write it down, then we can at least have a fighting chance of applying this method. So there's nothing random about this function. And it's an increasing function, or technically non-decreasing. They're sort of fussing about flat areas and stuff like that, but that just introduces a bunch of complexity. So that we will, for all of the examples that we will be doing, which will be mostly, at least in the beginning, for some continuous ones, in the continuous distributions that we'll be looking at, we only have to consider the CDF in the place where the PDF is actually there. We'll see what that's about. But the point is that not every function has an inverse. So, for example, this function doesn't have an inverse. Why? Because if I want, what is the inverse of this value? Well, there are two of them, so it's not uniquely defined. Or look at a sine function. And what's the inverse of, oh, I don't know, say 0 of a sine function? Well, there are infinitely many points that are the inverse of a sine function. So that, so if a function isn't monotone, meaning it only goes up or only goes down, then you in general you can't find the inverse. But the CDF actually is kind of increasing. Now, is it obvious that it's increased, that if I compare, how do you sort of realize that? So if I have a value y that's bigger than x, then is it true that the probability x less than or equal to x is going to be, well, less than or equal to the probability that x is less than or equal to y? Is that obvious? No. Why? Because I have more. The probability that it's less than or equal to y, I mean, it has all the probability here, and it may have some more. And so what that means is it's an increasing function, and so increasing functions have an inverse. And so what's the inverse? Well, if u is the argument of the range of our function, then the inverse is going to be the value at which it is. So, all right. So how do we get the inverse of a function? Well, how do you get a function in the first place? Well, you pick a place on the x-axis and then find where it hits on the y-axis, on the vertical place. So how do you find the inverse? You just flip it. So I pick a point on the vertical axis and then draw, conceptually, you can draw a horizontal line until it hits the function. And then when you drop down, the value on the horizontal axis, where that is going to be the inverse of it. I mean, this. Okay. Now, just some properties of the inverse. If we, the inverse is literally the inverse of the function, so that if we take the inverse, if we take the inverse of the inverse, then it's, well, actually, this should be x. It's sort of, that should be x. So the, if I have f of x and I take the inverse of that, then I just get x back. And likewise, if I have the inverse and then I take the function of that, then I'm just going to get my my value again. In other words, the inverse sort of cancels out the function. Okay, so and for some reason they don't, the math classes don't sort of talk about this. I mean, do you remember in a math class ever having to compute the inverse of a function? Oh, you do? Oh, okay. Well, good. All right. So, all right. So we're going to see some examples of this. But okay, so why go through all of this? All right. So we have a reminder about some of the properties of random variables, because if we're using them in a simulation, it's that's one of the reasons why we torture you with those probability classes, because it really is very useful. If you have a situation in which there is randomness and you want to model that, then you'd better have a good handle on what randomness is and how to characterize that. Okay. So here's another property of random variables. If if I have a random variable x and a function f, now this is just a generic function, not a PDF or anything, then but if I take that random variable and I shove it into my function, then what is this? So if this is a random variable, or RV will often, remember, RV doesn't stand for like Winnebago, it's random variable. So now what is this thing? See, this this is just an ordinary function. But what is this thing? That's a random variable. This is a random variable. In other words, if I take a random variable, I'm calling it x, I say this is a random variable, I'm going to apply a function to it. And what is the result of that? The result of that's another random variable. So, therefore, let's say I have a uniform 0, 1 random variable, just to pick one totally at random. Now I have this other random variable x that I'm interested in, and that random variable x has a CDF, and that CDF has an inverse because it's monotone, and this inverse is just an ordinary function. And so if I take an ordinary function and I apply it to a random variable, then what do I get? Another random variable, right? Am I going too slow? Okay. Now remember, every random variable has a CDF, a cumulative distribution function. And it turns out that the cumulative distribution function of this random variable is this, the CDF that I was interested in the first place. Now, is that kind of obvious? Maybe, no? Do you believe it? Well, I mean, there's believing it, and then there's pressing the I believe button. Somebody said it. So, so do you believe it, or do you believe it because I said it? And as you may have noticed, sometimes things I say aren't always true. So, not that I deliberately do that. I mean, it's just sometimes I make mistakes. Well, okay. So for now, let's just sort of press the I believe button on this. Are you okay with that? Okay. But you might want to give this some thought. It's one of these things where, well, here my experience is this. I mean, at first it seems impossible. And then if I think about it for a little bit, then it seems obvious. And then if I think about it a little bit more, it seems impossible again. So, but that's just me. So I hear there are drugs for that thing, but sort of thing. Okay, so I mean, in a sense, this solves the problem entirely. Remember, what was our problem? Our problem is we have a bunch of these things, and we want things that have this CDF, and now here's our solution. So we've got a sequence of these, and so if we simply apply this inverse CDF or the random variable that we want to these things, then we have the distribution that we want. Okay, assuming that you believe this. All right. Well, let's look at an example. Okay. Now I'm saying recall that the CDF for the uniform from A to B is this. You may or may not recall that. So kind of let's just sort of check that a little bit. So what is the let's remind ourselves about what are the properties of a probability density function. So this is what's so damn uniform about the uniform distribution? Well, it's called uniform because the PDF, the probability density function, is uniform, meaning it's sort of constant. Now, since we're kind of in the realm of continuous random variables, what is an important property of probability density function? In particular, what is the area? What is the area under a PDF? It's always 1. Why? Because the PDF is just a function which, when you integrate it, will give you probabilities. And if you integrate the whole thing, you better get 1. Okay. So if this is our PDF, then what would the CDF be? Let me just. Well, now the thing to understand is that both these PDFs and CDFs are defined over the entire real line. That isn't always emphasized a lot, depending on the probability course you take. So if we pick an X that's less than A, less than our minimum size, what is the probability that our random variable is going to be less than or equal to this value of X? Is it clear it's going to be 0? Right. And if we pick an X up here that's bigger than all of it, isn't it clear that the probability that it's less than or equal to that is going to be 1? Because it's going to. All right, so that was the easy one. What if we pick a probability that's in here? Now, strictly speaking, the CDF is actually the integral from minus infinity up to X of our density. Now, to give a different variable of integration. So if this is our PDF, then this is another way of describing the probability it's less than or equal to X. Okay, but that's calculus. And just as with discrete event state transitions, what is the area under the curve to the left of this? Well, it's going to be the base times the height, right? All right, so what do we need to know? We need to know, well, the base is going to be X minus A, right? So what's the height? Well, we don't know that yet, but there's only one value that height can be that will allow the area to be 1. It's going to have to be 1 over B minus A, right? Because that's the only value that when, you know, the base times the height is going to be 1. That's the only thing it can be. And so this is the base. The height is 1 over B minus A. And that's what we have here. Okay. And then, you know, so strictly, this is where you can get sort of fussy about this, but in fact, it's only this this area in here that we have to worry about. So how do we find the okay, so that's our CDF. So what we want is we want the inverse CDF. So how do we find the inverse of a function? Well, we choose some value u. I'm using u instead of y just for reasons that should be clear. And we set that equal to our function. And then we solve for x. And so if this is x minus a over b minus a, we solve, so we take the b minus a over to the other side, and so we get x is equal to a plus b minus a times u. And that's our inverse function. And so our method is, and this is for historical reasons, our method, we would write like this. Is that we would start by generating our uniform, and I'm going to make this a capital U, because our convention is that capital letters are going to be the random variables, and lowercase are just going to be regular variables. And we're going to return plugging this random variable into that. So that would be A plus B minus A times this thing that we generated. Now here's something interesting. If I ask you to generate this, but didn't tell you any of this, I guarantee that 100% of you would have come up with this. Well, maybe 99%. I don't know. I mean, isn't this pretty obvious? You know, because a uniform 0, 1 is like this. And so, but if we want it from A to B, what do we have to do? We have to kind of stretch it and then shift it. So we have to stretch it so that the width is B minus A, and then shift it so that the lower 0 would go to A. So 0 goes to A, we add A, we stretch something, you just multiply it by the stretch factor. So, and I would be astonished if you hadn't done this already in the past for something. But now, okay, so why does it work? It works because this is actually the inverse transform method, which actually does work. So, okay, so this is what I just did by hand. Okay, so and as with my, as you might guess, for pretty much everything that I like to do, you start with the simplest one. This is the simplest non-trivial random variable I can do with this. This is the easiest CDF, you know, linear. Doesn't get any simpler than this. So what's the next most, or a constant PDF. So what's the next most complicated one? Well, the next most complicated one would be a triangle. And now I have this, but I actually want to work this out for you, just to kind of show you that it's not. Okay, so can everybody see the whiteboard here? Okay, so here's the next most complicated one. So here's oops. Zoom leaves a little bit to be desired when it comes to this drawing program, but that's okay. At least we're do something with it. All right. So here's a PDF. And I'm going to say that it's going to go from the origin up to here. So this is the PDF of a triangle distribution. Why is it the triangle distribution? Well, because its PDF is triangle. So in order to generate from a random variable having this distribution, I need to find the CDF and take its inverse. But I don't have that. What I have is I have the PDF. And in fact, I don't even have the PDF. I have sort of a picture of the PDF, and I need to figure out what it is. I need to figure out the functional form of this. Now, what's the functional form of a line going through the origin? Yeah, it would just be A times the x, and this would be for 0 less than x less than the upper limit is going to be b. So it's going to stop here, and then okay. So all right. So that's so I need to find what A is. Well, and in particular, so what other information I have? Usually, the other information you have is the area. So I need to know what the height of this thing is. That's kind of what I need. I need to know what the height is. I don't know that quite yet. However, what is the area of this has to be 1. And what's the area of a triangle? Well, it's 1/2 the base times the height, and that has to equal 1, right? And so the height has to be equal to, boy, it's got the automatic. The height must be 2 over b. It should be a lowercase, but okay, so now what is the slope of a line going through the origin? It's rise over run, right? So A, how do you do that? I don't want you to capitalize it. Okay, so Y is the rise over run. So what's the rise? 2 over B times B, which is 2 over B squared. So our PDF is 2 over B squared times X, and that's good for X between 0 and B. Okay, so that's sort of fine and good, but then what I really want is I want the CDF, and the CDF is going to be, well, the integral somewhere. No, anyway, it's the integral, but I'm not going to do that because just as we had before, we have a little, if I choose an X value here, then now that I know what this height is, then what is the area? What is the area to the left of that value X? Well, it's going to be the base. And what's the base? Is X times the height. And what's the height? The height is f of X, which would be 2 over B squared times X. And so that would be, 2 B squared, and that would be, so 2x over B squared. Sorry, 2 squared X squared. And so that's our f of X is 2x squared over B squared. And that's between 0 and B. And so now, how do I, if I choose a U, that's the right value. I want a lowercase u. A lowercase u. I want a lowercase u, and you won't listen to me. Okay, so that is going to be our oh, wait, I forgot something here. Okay, this is a triangle, so it's actually 1/2 the base times the height. Which is not 2, but just X squared over B squared. So this would be X squared over B squared. And we want to solve for X. And so X squared is B squared times U. And so to do that, I now need to take the square root, well, or plus or minus, plus or minus the square root of B squared times U, which is actually, pull the B out because B is positive. but it's still plus or minus b times the square root of u. Okay, but I got two solutions. And is it, if I have a monotonic function, do I always get two solutions? No, so one of them is ectopic. And the question is, which one is it? And how do you figure that out? Well, one approach as well, negative is just so negative. So always throw out the negative. Not a good idea. What you do is you look for the support of the random variable. In this case, all the random variables generated are going to be positive just by construction. So I throw out the negative. So my inverse function is b times the square root of u. And so that's my method. So let's okay. So yeah, so that's so here the height was 2 over b, as we saw. The CDF is x squared over b squared, and then this is actually what I'm going to call a triangle, 0BB. We'll kind of get into what that is about, but we set u to be our f of x. We invert it. Only one solution, since the range is 0 to b, it's positive, it has to be positive. And so our inverse function is b times the square root of u. And so the method to generate from this is to start with the uniform and return that uniform times, take the square root of that uniform and return b. Now here's where things, you may have noticed that there are some things in probability that were, kind of obvious, pretty clear. And there were some things that were not. That's just the nature of probability. In fact, studies have shown that human beings are just notoriously bad at probability, even people who know what it is. And, just I'm terrible at probability in terms of real probability. And our intuition is not always that great. So now be honest, if I were to tell you this is how we're going to be generating a random variable, and I would ask you to predict what, if I were to generate 1 million of these and perform a histogram, what roughly would the shape of that be? Okay, so now, and if your intuition says triangle, then you're awesome. But my intuition says, it's probably going to look like that. That's what my intuition says. Why? Because that's square root function. Okay, now, so if your intuition says this, then bravo. But the fact is, and when we get around to implementing this, we'll just sort of do a check on this, because in my view, it's not intuitive at all. So it's kind of weird. And so, in other words, you can't tell from the thing itself what it's going to look like. At least those, even knowing this, and I learned this back when I was a grad student like you, and I still can't wrap my head around it, to be honest, because my intuition around it. Intellectually, I know this is true, but intuitively, it just doesn't make sense. So if that's where you are, then that's where most of us are. Okay, so so the next step is we've looked at really simple ones. We're going to start looking at some slightly more complex ones, and then one of the things that this brings up is, well, what this requires us to have a functional form of the CDF that we can actually invert. And the problem is that there are functions, or there are random variables that we can't do that with. So this takes us pretty far, but it doesn't take us all the way. It doesn't allow us to, well, just for example, like in your, when they talked about the normal distribution, and they talked about a bell-shaped curve, did they use the formulas for that? If you, or did they, was it kind of the field method? Do you remember the formula for the normal CDF? Just to kind of peek ahead, our friend, the normal CDF, remember the old bell-shaped curve, is going to look something like this. Let's just look at this to a standard normal at 0, and the PDF for this is 1 over the square root of 2 pi. That's not the important part, but it's e to the minus x squared over 2. And I mean, that's the bell-shaped curve. And the problem is that our CDF would be the integral from minus infinity to x of this. And you always have to use a different variable for integration. So this is that is the PDF, that's the CDF. So we can write down the PDF, and it's this amazing, elegant thing, sometimes called the Gaussian distribution because it was discovered by Laplace about a decade earlier. But this is as far as you can go. There's no functional form for this. And if there's no functional form for the CDF, then what hope do you have for the inverse? And pretty much, so in other words, here's an important distribution that we can't apply this to. So well, what good is it? Well, there are lots of distributions that we can't apply it to, and so we'll be looking at some of those. But this is to understand that we can't stop at just this inverse transform. We have to go further, and that we will do starting tomorrow.